Hey guys, we are finally out of the triple integrals section and we are starting off a new chapter, chapter 16 on vector calculus, and we're introducing this with vector fields. Now, just to give you guys an idea of where we're going, I had mentioned before that numerous times, Calculus 3, the whole point of this class is just to see what happens when we take calculus and pop it up to higher dimensions. Now, all the calculus stuff that we've been doing thus far with integrals, we've been spending a lot of time working with scalar functions. So maybe I have a function that I plug in x and y, or maybe I have a function that I plug in x, y, and z. Either way, those functions we've been integrating have been functions that spit out scalar values. So those are the things that we've been integrating before with, double and triple integrals. What I wanted to do in this chapter is we'll start taking a look at vector functions, okay, hence our need for these things called vector fields, because scalar functions aren't the only things that we may be interested in doing calculus on, okay? So just as a refresher, when I'm talking about vector quantities, what do I mean? Vectors are quantities that have both magnitude and direction. Big examples, velocity and force. So, what if I want to describe these quantities, okay, that end up being vectors? What if I want to describe them at several locations simultaneously? If you're wondering what the heck is she talking about, I can give you guys some examples here of maybe what I might be referring to. So things like, let's say that I want to consider things like electrical or magnetic or even gravitational fields, right? Gravitational, let me spell that correctly. These are kinds of things where we can have forces applied by objects. Maybe the forces might not be the same, at every location, right? Basic example, if I'm looking at Earth's gravitational field, sure, we have this idea gravity points down, but down for me is different from, down from someone in Australia, right? So different locations are going to induce different vectors related to that gravitational field. Other examples where maybe we might want to analyze things where we have different vectors at different locations. We can also consider things like fluid flows. When I say fluid, sometimes this encompasses more than people expect because, gases and liquids both count as fluids. So maybe you could have something like ocean currents be an obvious example of this, but air streams, traveling, air, what's going on with wind. That could be something that we would want to examine with a vector function as well, because again, depending on what position we're at, the wind might be doing something different or the currents might be doing something different, okay? So we've got some motivations for maybe why I might want to have functions that spit out vectors. What does my notation for this look like, and what are these objects really called? Well, here is why I gave you guys this, vector field as our section header here. A vector field is just its fancy name to say that we've got a vector function here, right? Now this is specifically the type of vector function that you take in an n-dimensional input and it spits out an n-dimensional output. Okay, so whenever I say vector field, that's all that I mean. Notice if I've got a vector field on 2 dimensions, I plug in a point, I have some sort of vector function, okay, that you plug in x and y there, and ultimately after plugging stuff into those component functions, you get a 2-dimensional vector back, right? So plug in a 2D point, get out a 2D object. Similar deal for 3-dimensional vector fields. Plug in a 3D coordinate, get out a 3D vector. Now, that's all well and good. We have an idea that, you can have functions and plug in different things and get out different things. What the heck does this actually look like? How might I try to, represent these things? Well, first off, I just want to touch on notation first. If we're talking written notation, You've already seen a snippet of this. My written notation for vector fields means that I have to use one of those arrow hats on the function, right? So, we already saw this on the previous page here. I gave you guys, f, and I had to stick a hat over it to denote that this thing spits out vector output. This is going to contrast with maybe what you might see in your textbook. Your textbook, they just use boldface notation to name these functions, but obviously it takes me a lot longer to sit here and make thicker lines to draw these letters out. So do note, boldface text, just like usual, that indicates a vector. Arrow hats, that indicates a vector. We're using that notation on our functions to denote that the output of f in these cases is going to be a vector. Now, as far as visualizing what these things look like, well, when I go to graph a vector field, how do I graph something that spits out functions? Well, what we do is you pick some sort of sample, okay, of points in your domain, and what you want to do is think about making a chart, right? Pick that sample of points in the domain. You can actually evaluate your vector field, okay, at these points. So you can figure out what vectors correspond to those points. And once you know what vectors correspond to those points, the way that we do the graph is you are going to plot, okay, at each of those points, the corresponding vector. Okay, the associated vector, right? So in other words, if I have, some sort of point, I'll draw a point here. I plug in that point, I get a particular vector that points off in some direction. Starting at that point, draw whatever vector that you had. We've mentioned before in the vector section that, vectors specify magnitude and direction. They don't necessarily care about starting points. We can kind of pick them up and put them wherever we need them to. We're going to pick these guys up and put them right on top of whatever that point is that we started with. Okay? So if I wanted to go ahead and actually try this with an example, let's see if I pull up my next example here. Here's a vector field. Let's see if we can sketch this, right? So I'm going to correct this here. I am using I and j to represent my standard basis vectors. Since this is 2D, I is just in the x direction, 1, 0, j is just in the y direction, 0, 1. So if you don't like that format, this is the same exact thing as if you write it this way, okay? Sketch that guy. Well, like I said, we want to start with a sampling of points in the domain. Now, I didn't really specify a domain here. It means that we get to take it to be basically all of R2, because we're dealing with 2D stuff. So I'm going to go ahead and just pick some sample points to evaluate at. Okay, let's go ahead and start out with I'll do some stuff that's pretty easy to plug in. Let's say I try a bunch of intercepts. I can try something like 1, 0, -1, 0, 0, 1, 0, -1. And then what I'm going to go ahead and do is see what happens if I actually plug in that point to my function, right? So I'll just go ahead and kind of talk through this here. For this very first point, we've got 1 is my x value and 0 is my y. That's going to knock off this first term here. Okay, but 1 was my x value, so I get a half. Similar here. We'll get 0 and negative a half because I've got a negative x. And then if I switch this around, for these guys, I have 0 as my x value. That'll knock off my second term here, so I'm just worried about what's going on with plugging in my y coordinate and the x component. Here I'm going to get minus a half, comma 0. And here I'm going to get, because my signs cancel, a half, comma 0. Okay, so again, what we said is at whatever your point is, what we want to go ahead and do is draw, emanating from that point, whatever the corresponding vector is. Okay, so if I just set up my xy plane, because again this is a 2D vector field, we are living in 2D here, starting at the point 1, 0, we'll go ahead and give you guys some scale here. Starting at the point 1, 0, I want to draw the vector 0, 1/2. Now that is the vector that goes 0 units in the x direction and 1/2 a unit in the y direction, positive y direction. So I'm going to get something that looks like this guy. Okay. Very similarly at -1, 0. So over here, I want to draw the vector 0, -1/2. At 0, 1, I want to draw the vector -1/2, 0. And at 0, -1, I want to draw the vector 1/2, 0. Now, this actually doesn't give me too much detail on this particular vector field here, so what I'm going to go ahead and note is, you know, for basically more information or a more detailed picture of your vector field, okay, for a more detailed pic of my vector field, sketch more vectors, basically use more sample points. So I'll go ahead and kind of fill this in here, okay, with maybe what this would look like if I drew a couple additional of these in. I don't want to bore you guys with making the table for this, but basically if I start filling in more points here, you'll notice that there's sort of this pattern that I've got with this particular vector field, that things sort of seem to be swirling about the origin. Okay, so that's basically what this vector field does. If we kind of add in more of these, if you wanted to make a table that was a little bit longer than what we got here, you know, add in more points, we can do that. Now as a comment, by and large, in the wild, if you're dealing with a vector field at all whatsoever, you're probably not going to be doing this by hand. These are kinds of the things that we do tend to have computers do for us just to make them go a little bit faster. And then another comment that I'm going to go ahead and make, especially if you're doing this in higher dimensions for like 3-dimensional vector fields, we can sketch these things in 3D too, but hopefully we recognize already that drawing stuff in 3D is kind of crappy to do by hand most of the time. Usually the drawing comes out a little bit wonky if you're trying to just eyeball this on your own. So usually these are things that we tend to have computers do. But just so you guys have reference and can kind of get a feel for what a 3D vector field would do, I'm going to go ahead and draw this constant vector field here. Okay, so again, 3-dimensional vector field, that means that we are living in R3 here. Since this is a constant function, right, basically what this is saying is at any XYZ coordinate, I plug in any point at all whatsoever in 3 space, it spits out the vector 1, 2, 3, right? So basically what this is at any point XYZ at all whatsoever, we're going to get that the corresponding vector is this 1, 2, 3 vector. Okay, so what I'm going to go ahead and do is we'll go ahead and start at the origin here, and just for reference sake, you know, this is the vector that goes 1 in the x direction, 2 in the y direction, and 3 in the z direction. Okay, so the way that we did this before when we were sketching stuff by hand was I tried to get a feel for like a reference box, you know, where exactly is the 1, 2, 3 point here. Okay, and the 1, 2, 3 point, if I draw my reference box that is 1 by 2 by 3, we're going to get back this point up top here. So that's going to suggest that this guy right here is my 1, 2, 3 vector. Now, as far as this being a graph of the, you know, vector field for f, we said that at any point xyz, the corresponding vector is that guy. So basically at any point that I would want to pick in 3 space here, I should be drawing back this exact same vector over and over and over and over again, right? So hopefully you guys get the point. I'm trying to make all of these guys parallel, pointing in the same direction, basically the same length, okay? Changing the initial starting position does not change my vector field. So notice, if this was describing some sort of like a force or like a fluid flow or something, okay, that's expressible in vector quantities, everything's going in the same direction, right? So we've kind of got a constant force is being applied here everywhere, a flow where like all of the particles are heading the same way at the same speed, okay? Now, like I said, 3-dimensional things, if you have anything much more complicated than this, probably harder to do by hand. Probably want to get a computer involved for stuff that's a little bit trickier than this if you're dealing with 3D. Now, what kinds of vector fields might I run into naturally? There is a special kind of vector field that we are going to run into a little bit later on that I want to touch on now, just so we've seen it. They're called gradient fields. Now, we've actually dealt with gradient fields before, it's just that I didn't call them a vector field before. You remember this little upside down triangle here was, if I take the gradient of f, this was me basically having you take that scalar function f, and then you take the x partial of it and then the y partial of it. Now, if this was a 3-dimensional function, you would also have a z partial on the end, so you'd get a 3D vector. But basically, it's a special kind of vector field, right? Whenever we took the gradient, we had a vector that had a whole bunch of functions on the inside of it, scalar functions on the inside of it. So basically, the gradient is a vector field. So just to note that, again, if you have a scalar function of 2 variables, your gradient field is going to spit out a 2D vector. If you have a scalar function of 3 variables, it is going to spit out a 3D vector. And we call these things gradient fields. Now, just as an example here, let's see if we can find the gradient field for this function and also sketch it, okay? Now, again, if I want the gradient vector field, all I'm asking for is, what the heck is the gradient? Well, my gradient is going to be the vector that contains the x partial and the y partial. There's no z partial because for this function there's no z. So if I want to go and take my x partial here, you will have to apply chain rule to this particular function. You will get basically, since this is x squared plus y squared to the 1/2, you will get 1/2 times this thing to the negative 1/2. So basically that square root's going to now be in the denominator. That's the derivative of the outside function. You need to tack on the derivative of the inside function. If you're doing this with respect to fx, or with respect to x, you're going to get a 2x to tack on. Similar deal, if I apply chain rule over here, we're going to get a very similar looking derivative. This is 1/2 times that same square root. But this time, if we're doing a y partial, the thing we have to throw on the end is a 2y. Now, I can clean this up a little bit, maybe write this in a slightly nicer format. So ultimately, what I've got is x over this square root, comma, y over this square root, okay? This is my gradient for f, okay? So we have found the gradient vector field, so as far as, that initial request for this problem, done, okay? We've got this vector function, okay, that spits out vector output. The second request is for me to sketch the field. Now, y'all saw that even for that really basic looking linear kind of function, sketching can go kind of slow. So I could sit here and just plot a bunch of points and shove all these in, and this is kind of a tedious function that's more complicated than the one before for me to have to compute at a bunch of locations. There's roots, I'm going to get decimals. What I'm going to suggest here is let's try to think smarter and not harder about this problem. I'm going to point out an observation here that'll hopefully make this a little bit easier to sketch. Okay, so if this is the vector field that I'm worried about sketching, here's my observation, right? I've got the same denominator in both of these components, so it kind of looks like I've basically got 1 over this square root x squared plus y squared here times a vector that's just got x and y in it. Now, as a comment, when you think about the vector xy and how this square root expression relates to it, really what we've got here is this looks a lot like the vector xy, and I just divided by the magnitude of xy. That is a much simpler way to think about this expression than this nasty thing that's got all the square roots in it. And the reason that I say that is this, okay? If we've got this vector divided by its magnitude, this means that pretty much every single one of my vectors are unit vectors. So all my vectors are going to be 1 unit long. That is one observation that I can make to help me with my sketch. Another observation that I can make is that my vector that is at any sort of point xy, well, this guy is going to point in the xy direction. Okay, just the thing on the bottom, all that division is doing is it's scaling it. Okay, I don't see any multiplications by negatives or any other weird functions. If all I'm doing is the scaling, I'm by a positive number. I'm not changing the direction. And another way further that I can interpret that, the fact that your vectors at xy point in the xy direction, what that's really telling you is that these guys are all going to point away from the origin, okay? So, directly away from the origin. Let's see if I can piece all of that together here, right? If I wanted to try and sketch this thing, let's say that I'm at 1, 1, okay? What that means is I want the unit vector that points in the 1, 1 direction. So this is not going to quite make it all the way to 2, 2, okay? Because, that distance is square root 2. We want to be a little shorter than that. I'll get kind of a similar looking vector over here at -1, 1. I will get a similar looking vector down here at -1, -1. Okay, notice all of these are pointing away from the origin. And then, if I wanted to go on my intercepts, here at 1, 0, I want the unit vector pointing in the direction of 1, 0. Okay, similar here, 0, 1, I want the unit vector pointing in the direction of 0, 1. So pretty much, just like I said, what's happening is, any point that we're at, you want to head straight away from the origin, okay, just radiating out from the origin. Every single one of these guys is going to be a unit long. Okay, so we've kind of got this like starburst thing where everything is trying to flee the origin as quickly as possible, but all of these are unit vector length. Okay, so this is going to be my gradient vector field right here. That's my graph of it. Now, question, because I did say that we'd be talking about these gradient fields again, so I want to be pretty comfortable with them. How does a gradient relate to its actual function, right? So like here, I started out looking at that square root of x squared plus y squared function the last time, and I had you guys actually graph the gradient. So how do those connect, right? Now recall, and this is a thing to dust off when we talked about the gradient in the first place, my gradient should point in the direction of maximum increase for your surface for f of x, or f of xy. Okay, so this points in the direction of maximum increase for your function f. If we're talking about something that's a 2D function, kind of like I've named here, you know, what that's going to suggest is if you had a contour plot, right? That was how we demonstrated this before. You know, if you plot the contour, let me spell this correctly here. If you plot your contours for your function f of x is kind of like your contour map for your surface. These gradient vectors, okay, the vectors in your gradient field should point orthogonal to those contour lines. Okay, these guys point orthogonal to my contours. Okay, you know, for example, if I had a whole bunch of these, you know, contour lines that were supposed to represent maybe, say, like a mountain or something, and I want to figure out what's the steepest way up the mountain, you know, we don't want to go on some sort of meandering path that has us wobbling around. That's not the fastest way up. That's not the direction of maximum increase. What we would want to do is, you know, if we want to go as fast up as possible, you want to head orthogonal, okay, to these contour lines, right? So head at right angles to those. Now, let's see if we can actually apply this to the example that we just looked at. We started before with this function, root x squared plus y squared. We played around with the gradient and found that this is what it looked like. Okay, we had that thing where everything pointed off, you know, away from the origin. Well, let's think about this here. This is actually a named surface for us. We played around with it a little bit, you know, in our triple integral section, because when you go to plot this thing, that's a cone, right? So here, if that guy is a cone, okay, so here's my x and here's my y, notice that when I go to do my contour plot for this thing, well, my contour plot for this is going to highlight my curves along which I have level heights, hence level curves. This is going to highlight my curves of level heights for this function. Now, if I want to get level heights here along this curve, okay, and take horizontal cross slices of this thing, and then look down at those curves from above, we're just going to be seeing a bunch of concentric circles. So let's think about this. I'm saying that here, if I move, that's a crappy circle, let's fix that one. If I have these concentric circles, kind of got this bullseye thing going for my contour plot, well, we said before, all of my vector field vectors basically head straight out and away from the origin, right? So all of these were heading away. And notice that when these vectors head away, they end up being at right angles to my contours. And further, if we have all of our vectors heading outward from the origin, okay, so if we've got this general pattern that everything's heading away, of course that's the direction of steepest increase for my surface, right? If you're trying to climb your way out of this cone, what do you want to do? You want to head away from the origin, okay? That's going to be your fastest way out of this thing. That is your direction of steepest increase, okay? Now, other comments on properties of vector fields that we should be familiar with, because they're things that we might run into later. I will point out to you guys this property of some vector fields, not all of them, about them being called conservative or not conservative. This has nothing to do with political leanings or anything like that. What I mean by a vector field being conservative is that it's the gradient of some sort of scalar function. So what I'm getting at here is if I tossed you some sort of a vector field and we can obtain that vector field by taking a gradient of something, then we get a conservative vector field. And in that case, if there is some sort of corresponding scalar function that you took a gradient of to get that capital F in the first place, well, we're going to call that guy a potential function. Okay, so basically what I'm really getting at here is, can I find some sort of a little f that when you take a gradient of it, you get this capital F. And again, I'll go ahead and make the observation. You can apply this to both the 2D and 3D vector fields. But, okay, not all of them are going to have this property. Okay, not all of them will have this property. I'll try and touch on an example real quick here. We've seen this before. This was basically the gradient that we got when we took the gradient of that cone, right? So if this is my vector field, two conclusions that I can make here. First off, sure, F is conservative. And this is because if you go to take the gradient of that square root of x squared plus y squared function, you're going to get F back, okay? So what this is going to tell me, okay, in terms of the terminology that we used above, this function, this square root thing, this guy is a potential function for this f. Okay, and since this isn't necessarily the the only function we're going to run into, I don't want to keep beating this particular example into the ground. How might I look at a vector field f and try and check whether or not it's conservative? How might I be able to tell? Because here, it was a coincidence. We had already seen that the gradient of this was supposed to be this function. How might I try this for an independent example, right? Maybe I give you something like this guy and I ask, is this conservative? Well, really what I'm asking for here is, if I'm trying to see if it looks like a gradient, okay, does this guy look like the gradient of some f of x, y, z? Okay, or another way that I can phrase this is, does it look a lot like I took a bunch of partials, right? Does it look like an fx, an fy, and an fz for some f? Now, I can actually check this, right? Let's verify, right? And the way that I'll suggest that we verify for now, there are other techniques we can run into later on, but for now, if it was a collection of partials like this, what that sort of suggests is you should be able to use partial integration and double check what f you get back if there is an f that this works for, right? So does, integrating this first piece with respect to x give you the same f as you could get back from integrating the second piece with respect to y, or this thing with respect to z, right? So I'm going to take an antiderivative of this first component. Hopefully this looks like antiderivative of fx with respect to x, and then I get some f back. I can check this other piece with respect to y, and then I can check this last piece with respect to z, okay? So if I actually compute these, let's double check. My antiderivative with respect to x here, I will get an x squared, y squared. This is indefinite though, so I'm going to point out we might get some sort of a constant of integration, but the catch is that for constants of integrations with these guys, well, we antiderived with respect to x. That meant that in that case, anything in terms of y and z is constant. So maybe you don't necessarily just get a plus c on the end here. You might actually get a function of those other variables. Okay, similar thing down here. If you go to take this antiderivative with respect to y, you know, my antiderivative there, again, I'll also get x squared y, but in this particular case, y was my variable, so that means that here x and z are going to be constants. Okay, and then this last one, this is maybe a little strange here because, you know, I'm integrating 0. I don't usually get that. Another way to think about it is, what do you have to derive to get 0? You usually think that's a constant, but what's a constant in terms of z being a variable? Well, the stuff that's constant in terms of z being a variable is anything in terms of x, y. Now, all of these look very, very different. The catch is that if this was really my fx anti-derived with respect to x, my fy anti-derived with respect to y, and my fz anti-derived with respect to z, I should be able to reconcile this as one singular function, right? So I should be able to reconcile this as some sort of function f. Now, notice, I can actually do that, right? The reason that I say that is if I let these guys be basically the same thing, plus maybe some sort of actual legitimate c on the end here, I can go ahead and reconcile these guys as basically the same thing, right? If the only thing that involves x's and y's is x squared plus y, oops, had my antiderivative wrong here, x squared plus y squared, and then maybe I have some sort of constant on the end, then sure, okay? This work is going to suggest that if I go ahead and make that assumption, you know, x squared, y squared, plus some c on the end, that guy is going to be a good potential function. Okay, and you can even check if you're worried about having found a good potential function or not. You can actually take the partials, right? Your x partial of this expression gives you that exact x component that we started with. The y partial of this expression gives you the exact y component that we started with. And then since we had x squared, y squared plus a constant, of course the z partial of that's going to be 0. Okay, so we just reconciled that, you know, when we anti-derived trying to get f in each of these cases, we were just writing f in different ways. Okay, so the beginning part involved my x and y terms, and here maybe we might have had a constant on the end for my remainder of my function.